Okay, now where is that square? It's got to be around here somewhere. Oh, there it is. Aw, man. Don't you hate it when your stuff gets rusty like this? This calls for something special. The Rustinator. The Derustinator. Alright, let's see what we can do as far as derusting things. Electrolytic, does that look like coffee or something? That doesn't look right. And let's see here. Iron anodes, that's a little bit odd. Oh my god, that thing looks like it's... don't even want to know what thing about that. Sacrificial anodes. And wait a minute, that's a battery charger. What on earth is going on? Look at all the bubbles on that thing. This is definitely not right. Wow, this is a cornucopia of bad ways to do this. So to understand why it's better to be using a base solution rather than acid solution for this electrolytic reduction of the iron or the rust, we have to look at a Porbet diagram. And so this is the diagram for iron and water, and basically what you're looking at is the x-axis is the pH, so we can go from our neutral around 7, and the y-axis is the voltage that is applied to the electrode or to the iron relative to a reference. And so we don't have to worry about the exact values on that, but basically we're going to say, all right, relative to the rust just sitting there without anything happening, we can kind of figure out where this is going to be, and we follow that through. I think I must not have hit that quite right, because this should actually be sitting somewhere in here. And maybe that I'm wrong on exactly where that should that potential should be. But the point of it is that the iron oxide is a stable material, so even if it was sitting in water, it's not going to go and dissolve on its own. And so we should be seeing something where it's in this. So if you see this sort of big polygon here, this is an example of, iron 3 oxide. So because we see a 3 on this, we can work out basically that that's going to be the iron 3 form. And so this is your standard red rust. The NH2O just means that there's some water that is accompanying that. It's basically in the solid. Anywhere where you see a plus or a minus here is an indication that that is an ion, which means it's in solution. So now, here's the thing. We're starting off in that spot that I circled, somewhere in this area. And we're trying to get to here. So the thing is, if we don't want to lose any of the iron, so if we want some chance of getting the iron back rather than just dissolving the rust away, then we cannot go into a solution. I mean, technically we might be able to, and we'd end up just plating the iron back on, but if we don't want to get it dissolved, then we need to find a route that follows through something that is only going to be in solid form. So, if I take a look at this, going with an acid, is going to take me in this direction, which frankly shouldn't be that surprising. If I put iron oxide into an acid, I'm going to expect it to dissolve. And then applying a bias to get it down to here, that is the route that's going to end up dissolving the acid while it gets to this point. The other option is we go for a sufficiently basic solution, and then when we apply the bias, we will go through stages that are entirely solid state, so no ions involved in this. It won't dissolve. So from this perspective, it makes more sense to go with a heavily basic solution, which is why I picked something that has a pH of around 11, and that pretty safely gets us into that range there. So that's one reason why it doesn't make a lot of sense to use an acid. Maybe it's splitting hairs because of what I said. If the rust isn't that much, or some of the rust is going to flake off anyways, then yeah, I guess you could do the acid. But from my perspective on this, it makes more sense to go with the base so that you can truly reverse the rust rather than dissolve it off and then maybe somehow electroplate it back on. So let's talk about that battery charger and why that's actually a really awful idea. So imagine that we're starting, we've got a pH of 11 and we have no bias on it. It's just going to sit there, it'll stay rust, nothing else. So we do need to apply a voltage to pull this down until we get into this area here. But if you take a look at the voltage on that, it's only like not even 1 volt. Now, admittedly, there's going to be resistance in the electrolyte and everything else, so it's not going to work on just 0.8 volts. You're going to need a little more. My experience is that's about 2.3 volts that's required. But that's a far cry from 12 volts. And so the question becomes, well, what happens to the extra voltage? Is that just more power? Is it going to happen faster or something? No. Because the way the battery charger is working is it is going to be legitimately trying to put 12 volts onto there. It may not necessarily make it to that, but it's going to sure try. And the issue here is that electrochemistry would allow an additional reaction to occur if you have more voltage, and that extra reaction is going to generate hydrogen. And those bubbles that you see coming off of the rusty object when this is being produced is exactly that. It's hydrogen bubbles. A lot of the YouTube videos acknowledge that and then tell you that you should do this in an area where there's adequate ventilation and whatnot. And fine, you could do that, but you're wasting electricity among other things, and second of all, you're kind of creating something a little dangerous, because how do you know for sure that you're not pooling up hydrogen somewhere? You can't smell it, you can't see it, and it would gather up at the ceiling, and so the next time you flick your lights on, it might go boom. And it just doesn't make any sense to do that, because it's not necessary. Now this last part is this issue of people talking about a sacrificial electrode. I don't know, maybe it's just some cult that I'm not aware of, praying to a god of steel or something. I'm not really sure, but this isn't really what's going on here. You don't need a sacrificial electrode. So if you have your rusty object here and you have another electrode, now what's going to be happening is you have in here, say, Fe3O2, and you're trying to reduce that down to iron, which means that you're getting oxygen ions being pulled into the solution. Now, the electrochemists in the audience, you can just don't worry, I'm trying to make a simple explanation on this. Feel free to comment about what I'm saying wrong here. Now, those ions are going to eventually make their way over to here, and what's going to end up happening is that oxygen ion is going to get reduced to oxygen molecules, and those would bubble away. So you don't need, this oxygen doesn't need to get stored somewhere, you just put it back in the atmosphere. And so if you choose something like a piece of iron, then yeah, of course, what's going to happen? This stuff is going to start rusting and form its own iron. And that's how you end up with something that looks like coffee or I don't know what. So it's really not necessary. And instead, all you have to do is use something that's conductive but not reactive. And the easiest one to do that is to use graphite. I do agree very much with what people say of do not use stainless steel. That is really a bad idea because not only are you going to cause rust, but you're also going to create hexavalent chromium, which is really nasty stuff. So just don't do that. So I'm going to go ahead and do the electrolytic rust removal. Still electronic anyways. On this pair of needle nose pliers here. And it's one of the more rusty things I happen to have. And the solution that I'm going to be using on this is a 2 molar sodium hydroxide. So you do not want to get this on your skin. And with a graphite electrode. And my power supply for it is just a little wall wart because I really don't need all that much power on this. So my goal here is to see the oxygen bubbling on the anode there and to see next to no hydrogen on the cathode, which is the part that we're trying to derust. If I'm generating hydrogen, that's actually being wasted, so I want to be just below that, but the best way for me to tell is to just have a little bit of bubbles coming off. Now, one thing I've noticed is after the first few minutes, especially when I see that much bubbling, there will start to be a lot of hydrogen formed, and so I have to turn down the voltage just a little bit so that I can get it back to that just barely bubbling state. Okay, this has been sitting in there for a couple of hours, so time to take it out and see what it looks like. One thing I want you to notice is that the solution, and I've been using this for a couple days now, is definitely has some chunks of rust that fell off, but the solution itself is actually pretty clear. So that gives you some indication of the fact that if you do this right, then your solution shouldn't have any iron ions in it. All right, so put this into some water. Rinse that off. Take that off and take a look and see how is it looking. Definitely see parts that are now just steel without any rust, and spring looks a lot better. And I can tell you right now, this is opening and closing much easier. So much so that It used to be so rusted that I could close it and it would stay closed, but now you can see that's not the case. So that looks pretty good. I'm going to rinse it in some more water, and then what I'm going to do is wipe it down, and we'll get another look at that. Okay, so what I'm going to do is we're going to just wipe this down, and one of the things that you're going to see is that I will get some bit of black material off, and that's going to just be some of the magnetite that was formed but not reduced. And I think the main reason why it doesn't get reduced is because it becomes electrically isolated from the steel, because the honest truth is this isn't nearly enough, at least in my opinion, to account for all the rust. So, you know, because I'm sure somebody could be looking at this and saying, oh yeah, all he's doing is just, you know, loosening up the rust and not actually converting it back to iron. And I'm arguing that that's not the case, and certainly the electrochemistry would argue that too. So, yeah, I mean, if you take a look at that, you can definitely see that there is some steel exposed there. And, you know, I'm not really rubbing this very strongly here, so it definitely does get a black patina on it, which again would be coming from the magnetite that's been formed. And, you know, it depends on aesthetics. From my perspective, I don't see that as a problem. If anything, it's a slight protective covering on this, but you know, take a look at that. That's really not bad. You know, I could maybe try to hit it with a little bit of, say, Scotch-Brite and see what that does, but I think it's going to be diminishing returns because any of the film that's still on there should actually be bonded pretty well. So, yeah, I mean, that cleaned it up a little bit more, but, you know, the thing that's really nice about this is just the fact that this is, I mean, like I said, this was rusted, and it was definitely not doing this kind of thing before. And so it's really cool because you can put that in there, and you don't have to take it apart, and it's, everything basically gets in there. So it's quite nice. You do have to really make sure you rinse everything off. It doesn't hurt to hit this with a little WD-40 afterwards. A little, you know, sort of side note on that, and I didn't know this until a while ago, the WD in WD-40 is water displacing. So it's not, it actually makes a really crappy lubricant unless you're planning on using it for a very short time. But if you've got a part that has water on it, then hitting it with a little bit of WD-40 will displace that water. So that's actually what it was meant for. So you can work that in a little bit and then basically wipe it off. And like I said, it makes a really lousy long-term lubricant there. But the reason why I want to do that is trying to get it into these little working areas that are so close. There's probably was still some water in there, and if the water displacing aspect of the WD-40 did its job, then that shouldn't be the case anymore. So now I got one other one that I want to just show to give a really good indication of just how well this stuff works. This is a piece that I put in earlier today, and the solution only went up to here, so you can see the clear difference between the original rust and what you have on this side. And, you know, short of me going to my lab and getting my atomic force microscope or something, I'm not going to be able to make a real assessment on what happened at that surface, but it would be fairly reasonable to say that that rust actually got turned back into the iron. So, all right. So I think this is actually a very worthwhile technique. Like I said, it's not something that's new. Lots of people are doing it, but they're doing it wrong. So hopefully this will show you how to do it the right way.